Hello there and welcome back to the Science Sleepy Minds. You float, weightless, inside a room that shouldn't exist. Around you, glowing coils hum with a sound just below hearing. At the centre of the chamber, suspended in an invisible magnetic web, a single, golden droplet hovers. Except it's not gold. It's not anything really. It's antimatter, one rogue atom away from touching normal matter, and the entire chamber would go out in a flash of light so pure it'd make a supernova feel bashful. But for now, you're safe. Probably. This is antimatter. You're incredibly volatile, almost impossible to make, definitely impossible to store new best friend. The thing is, it's not fiction. It's real. It's been made in labs. We know it works. And it might, if everything goes right, be the fuel that takes us to the stars. You probably won't survive this, by the way. Not because of antimatter, just because space is that big and weird. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know in the comments where you're listening from and what time it is there. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You start at the very beginning, where things are still calm, normal, Newtonian. Atoms made of protons, neutrons and electrons. No drama, no science fiction vibes. Just your average building blocks of the universe. But here's the thing, for every particle of matter there exists, or should exist, an equal and opposite particle. Same mass, same spin, opposite charge. Mirror twins, basically. And when they meet, well, they don't hug. They obliterate each other. That's what we call annihilation. And it releases a ridiculous amount of energy. So how does something like this even exist? And how did we find out about it without, vaporizing ourselves by accident? We go back to the early 1930s, when physicists were just starting to figure out the quantum chaos happening at the tiniest scales. Paul Dirac, the guy whose forehead probably had its own postal code, proposed a weird new equation that suggested electrons might have a shadowy twin. One with the same mass, but a positive charge. This wasn't just math messing around. In 1932, Carl Anderson spotted the very first antimatter particle, the positron, while looking at cosmic rays in a cloud chamber. It curved the wrong way in a magnetic field. That's it. That little loop changed everything. Of course, we didn't get annihilated, thankfully. Positrons get created naturally in some radioactive decays and even inside thunderstorms. Yes, you heard that right. Lightning sometimes makes antimatter. Nature's kind of metal like that. But here's the big head scratcher. If every particle has an antiparticle, and the Big Bang created both, then why isn't the universe just a simmering soup of radiation from all that mutual annihilation? Historians still argue whether the early universe had a tiny imbalance in matter over antimatter, just enough to leave us with, well, everything. If it had been equal, there'd be nothing left but cold gamma rays and disappointment. That's why scientists sometimes refer to antimatter as the missing half of the universe. It's supposed to be here, but it's not. Unless you count a few rogue antiparticles zooming through space, or the handful we create in giant accelerators, it's like having a perfectly symmetrical twin who ghosted you at birth. But when we do make it, oh boy, it's powerful. Imagine you had a single gram of antimatter. Just 1 gram. Let it meet 1 gram of regular matter and boom. The energy released would be equivalent to about 43 kilotons of TNT, roughly 3 times the Hiroshima bomb. From a spoonful, that's not a fuel, that's a miracle weapon pretending to be science. Which brings us to its potential. Unlike chemical fuels, which are basically throwing a tantrum at the molecular level, antimatter gives you total conversion of mass to energy. That's E equals mc squared in its rawest, most unapologetic form. Chemical rockets are like hurling rocks with a slingshot. Antimatter, that's a direct email to the universe saying, let's get moving. Still, you can't help but wonder, if it's so good, why aren't we using it? Well, for starters, it's rare, like galactically rare. We can make about 10 nanograms of positrons per year globally. That's a billionth of a gram, enough to maybe pop a kernel of popcorn, if you're patient. And containment? That's the real bear trap. You can't just scoop antimatter into a tank. It touches the walls. It annihilates. So we float it in magnetic traps, in perfect vacuums, surrounded by layers of redundant systems, and even then, it might still wink out of existence with a sneeze. Still, we're getting better at this. The folks at CERN have held antihydrogen atoms for minutes at a time, an eternity in antimatter terms. You'll meet them more formally in the next section. They're the mad scientists of your bedtime story. As for you, you're drifting in orbit now, staring at Earth below and thinking about how silly our combustion engines really are. They burn stuff and shoot fire. Cute. But when you dream about future starships, you picture quiet, silvery vessels gliding on invisible exhaust trails of pure annihilation. Antimatter drives, whispering through space like ghosts with purpose. And you, maybe you're a bored one. Maybe you're watching a pellet of antihydrogen spiral down a magnetic chute, accelerating until it meets its partner and explodes. Not in fire, but in light. Propelling you forward, not with a roar, but a pulse. That's the dream. And yes, the risks are big, but the payoff? Even bigger. Tomorrow's ships aren't built from steel. They're built from patience, particles, and physics we barely understand. But we're inching closer, atom by atom, trap by trap, idea by idea. And it all started with one tiny particle, curving the wrong way. You hover now in a hazy lab from the early 1930s. Dust motes drift lazily in golden sunlight streaming through high windows. Somewhere in the corner, a coffee cup trembles slightly every time the building's generator kicks in. You drift closer to the main workstation, where a young physicist stands squinting at a glass container filled with supersaturated vapor. He's staring at a faint white streak, curved ever so slightly the wrong way. This, right here, is where the antimatter story truly begins. Welcome to Caltech, 1932. The physicist is Carl Anderson, and the device in front of him is a cloud chamber. Essentially, a particle trap that lets you see the invisible. It's a kind of primitive space canvas, where high-energy particles leave behind trails like contrails in the sky. Cosmic rays, those high-energy particles from space, slam into the chamber and leave marks behind, usually electrons, protons, that sort of thing. But one day, Anderson sees a streak that makes no sense. It curves like an electron, but in the opposite direction. Same mass. Opposite charge. Anderson stares at the trail like it just insulted his family. This shouldn't be here, but it is, and so he does what any reasonable scientist in the 1930s would do. He publishes it and names it. He calls it the positron, the positively charged electron. And just like that, the universe becomes twice as weird. This was the first direct evidence of antimatter, not theory, not math, just a squiggly line in a foggy box. The really weird part? The positron had already been predicted. Just a few years earlier, Paul Dirac had done the unthinkable, combined quantum mechanics and special relativity into one hideously elegant equation. It described the electron beautifully, but it also had a second solution, a mirror version. Instead of ignoring it like a math error, Dirac embraced it. He theorized that there must be a particle with the same mass as an electron but the opposite charge. The press at the time mocked him. They called it Dirac's folly. Turns out he was just a few years ahead of reality. Anderson's cloud chamber photo changed that. Dirac wasn't just right. He'd cracked open a door to a hidden half of the universe. That discovery earned both men Nobel Prizes and gave us our first glimpse of what we now call antimatter. What Anderson didn't realize at the time is that the universe was already creating these particles in plain sight. Positrons are produced naturally in certain types of radioactive decay, specifically in beta plus decay, where a proton turns into a neutron, spitting out a positron in the process. Even bananas, those innocent potassium-packed snacks, emit tiny amounts of positrons as their potassium-40 content decays. So yes, your breakfast might be a low-grade antimatter generator. And if you think that's wild, consider this. Lightning storms can also generate bursts of gamma radiation that result in positron production. Every time there's a big thunderclap somewhere high above the clouds, a miniature antimatter factory might be flickering to life. Nature doesn't need a PhD, it just needs a high enough voltage. But capturing that antimatter, that's a different story. You can't just put it in a jar. The moment a positron touches a regular electron, both vanish in a flare of gamma rays. So for decades, antimatter remained a curiosity, a clever quirk of particle physics. Something cool to talk about in lecture halls, but not something you'd build a rocket with. Not yet. Historians still argue whether Dirac truly believed his prediction could lead to usable fuel, or if he saw antimatter purely as a mathematical necessity. Either way, the genie was out of the bottle, and as science tends to do, it kept pushing forward. In the decades after Anderson's discovery, physicists began to look for more antiparticles, and they found them. Antiprotons came next, discovered in 1955 at UC Berkeley. Then antineutrons, antihydrogen, and beyond. With each new discovery, the symmetry of the universe became clearer and spookier. For every particle, an opposite. For every U, a theoretical anti-U. But here's a fun detour. There was a short-lived Cold War rumour that the Soviets were secretly trying to weaponize antimatter in the 1960s. The story goes that someone misread a physics paper and decided the US needed to investigate. This led to one of the most absurd internal memos in military history, suggesting that we might create antimatter grenades, which, given our containment abilities at the time, would have mostly just vaporized the grenade thrower. Still, you gotta admire the ambition. Back in the lab though, scientists were just trying to keep positrons around long enough to study them. This meant building bigger machines, cyclotrons, synchrotrons, and eventually the mighty Large Hadron Collider, all to smash particles together in the hopes of creating and isolating antiparticles. You glide forward in time now, hovering over increasingly complex particle detectors as humanity chases these elusive mirror particles like ghost hunters with degrees in thermodynamics. And when they do appear, it's always brief, nanoseconds, microseconds if you're lucky. But each sighting inches us closer to the dream, storing them, controlling them, using them. It's ironic, isn't it, that something so pure in energy, so efficient, so tantalizing, should also be so fragile. You can make antimatter, you just can't keep it, at least not for long, so here you are, floating through a quiet chamber of history. Carl Anderson's cloud chamber still hums somewhere in memory. That backward curved trail still glows in your mind like a fingerprint from another dimension. The first real evidence that our universe had a flipped version, just waiting to be explored. And from that tiny curve in the mist, everything else would follow. The particle accelerators, the lab traps, the theoretical drives, even the dreams of starships with no fuel tanks. Just tiny antimatter pellets flicked into reactors, sending travellers beyond our solar system. But for now, it's just a streak in a chamber. The first ripple in a story so strange, it might just be our future. You float now through the sleek subterranean corridors beneath Switzerland and France, home to one of the most mind-bending operations on Earth, CERN. More specifically, you're drifting gently through a lab known as the Antimatter Factory. Sounds dramatic, right? Like it should be lit with flickering green lights and echoing evil laughter. But it's actually astonishingly clean, fluorescent, and weirdly quiet for a place that produces annihilation on a daily basis. This is where we stop imagining antimatter as some future sci-fi dream and start seeing it as something tangible, measurable, and, if you've got a few $1 billion and a lot of magnets, somewhat manageable. At CERN, teams of physicists routinely create and trap antihydrogen atoms. Not a theory, not a comic book plot. Real, physical, antimatter atoms, held in place by magnetic fields and studied down to the femtosecond. Let's get cozy with how that works. First, the basics. Hydrogen, the most basic element in the universe, is made of one proton and one electron. Flip that, and you've got antihydrogen, one antiproton, one positron. The antiproton has a negative charge, the positron a positive one. Combine them in the right conditions and voila, a perfect mirror of ordinary hydrogen, ready to explode on contact with regular matter. You know, just casual Tuesday stuff. Here's where it gets spooky cool. You can't just shove a positron and antiproton together and hope they click like interstellar Lego. You need to slow them down, a lot, because particles don't like to settle down. They're hyper. So CERN uses what's called the antiproton decelerator, a circular track where high-speed antiprotons are gradually slowed using electric and magnetic fields. It's like trying to get a caffeine-riddled squirrel to nap in a hammock. Once calm enough, these antiprotons are merged with positrons inside a vacuum chamber. If all goes well, they briefly become antihydrogen. And here's where the magic, or anxiety, happens. Because even a single atom of antihydrogen that touches the container walls will instantly annihilate. So, to avoid a very tiny but very expensive disaster, scientists trap the antihydrogen in a magnetic bottle. A set of finely tuned fields that prevent the antimatter from ever physically touching anything. Imagine juggling soap bubbles inside a porcupine cage, and now the bubbles explode on contact. That's the vibe, but they've pulled it off. In 2011, CERN's alpha collaboration managed to trap antihydrogen atoms for over 15 minutes. That may not sound like much, but in particle physics it's practically an eternity. Long enough to study the spectral lines of antihydrogen, compare them to those of hydrogen, and start poking at one of the biggest questions in physics. Why does regular matter dominate the universe? Because remember, we don't really know. The standard model of particle physics says matter and antimatter were created in equal amounts at the Big Bang. But clearly, we're living in a matter-dominated universe. You're not made of antihydrogen. Your phone isn't powered by anti-electrons. You don't brush your teeth with anti-toothpaste. Something tipped the balance early on, and we don't know what. Historians of science and physicists themselves still argue whether it was a random statistical fluke or some hidden asymmetry in the laws of nature. So CERN is doing more than building particle playgrounds. It's probing the very reason you exist instead of being a brief flash of gamma rays. But let's zoom out for a second. What's it like in this antimatter factory? Well, the facility itself looks more like a corporate campus than a Bond villain lair. Smooth floors, cable runs overhead, scientists in lab coats tapping on laptops and sipping questionable coffee. The machines do the flashy stuff. Circular accelerators spin particles at near-light speeds. Traps hum and click with electromagnetic rhythms. Radiation signs glow cheerfully at you, just in case you forgot that the building produces microcosmic fireballs on a regular basis. It's the kind of place where even a sneeze would be double-checked with a Geiger counter. Still, it's not perfect. Despite the breathtaking precision, CERN can only produce trillions of antiprotons per hour, and even that equates to mere nanograms of antimatter. Why? Because most of the energy goes into just making the things, not keeping them. It takes an enormous amount of power to produce a fraction of what you'd need for even a single propulsion test. In fact, creating 1 gram of antimatter, enough to power a very small antimatter engine for a very short time, would take about 25 million billion joules of energy and cost an estimated $62 trillion. So, a little outside your monthly budget. Still, the progress is mind-bending, not just because we're making antimatter, but because we're holding on to it, trapping it, studying it with such finesse that researchers have even started to measure how it falls. That's right, they're trying to see if antimatter falls down or up in a gravitational field. Most evidence points to down, because gravity doesn't care whether you're made of atoms or anti-atoms, but until recently we hadn't actually observed it. That test, known as the Alpha-G experiment, is still ongoing, and honestly, the fact that we don't yet know if antimatter behaves identically to matter under gravity, that's not a failure. That's the good stuff. That's the delicious uncertainty where breakthroughs happen. Meanwhile, fringe theorists whisper about antimatter propulsion, gathering in corners of the internet with diagrams of impossible spaceships and acceleration curves that defy conventional fuel physics. And while most of those dreams are still technically impossible, places like CERN keep turning fantasy into possibility. One trapped atom at a time. So you glide now past one of those antihydrogen traps, where invisible particles hover like phantoms. Scientists monitor magnetic field readouts and particle decay patterns. They're calm, focused, the kind of people who trust that 6 decimal places just isn't accurate enough. Somewhere in this underground maze, a positron hums in place, its job simply to exist without touching anything. It has no idea that humans are placing all their deep space hopes on it, that this little dot of anti-you might one day light up the sky, not with fire, but with annihilation-powered motion. From a quirk of quantum math to a real floating atom of not matter, you've now seen how antimatter isn't fiction. It's science. Complicated, expensive, breathtaking science. And it's only getting started. You're floating now outside the edge of Earth's atmosphere, looking down on a planet that still thinks chemical rockets are cutting edge. Below, a launch pad smokes and shakes as another booster rumbles upward, leaving behind a flaming trail and several tons of carbon emissions. Loud, messy, inefficient. The kind of propulsion that got us to the moon, barely. But out here, in the silence of space, you're here for something different. Something cleaner, smarter. Something powered by the most efficient energy exchange in the known universe. Let's talk about what makes antimatter propulsion so wildly powerful. Start with a thought experiment. You take a tiny bit of matter and an equal bit of antimatter, say a proton and an antiproton and let them meet. The moment they do, they annihilate. Completely. No ashes, no soot, no leftover atoms, just energy, released in the form of gamma rays and sometimes secondary particles like pions. And that energy doesn't just go boom. It's not an explosion in the chemical sense. It's a flash of pure Einstein-grade fire. Remember E equals mc squared? This is the gold standard example of it. Mass converted directly, totally, and efficiently into energy. For scale, if you annihilate 1 gram of antimatter with 1 gram of matter, the result is about 180 trillion joules of energy. That's roughly equivalent to 43 kilotons of TNT, like detonating 2 Hiroshima bombs in the span of a blink, from something the size of a sugar cube. By contrast, chemical rocket fuel converts only about 0.0000001% of its mass into thrust. It's the toddler of propulsion science, burning loud and bright, but mostly just flailing around. Antimatter, in theory, changes the entire paradigm. With it, we're no longer hauling enormous tanks full of cryogenic fuel for a few minutes of liftoff glory. Instead, a ship powered by antimatter could travel vast distances using a mere handful of grams, provided, of course, we can store it safely and harness its energy without vaporizing the crew. So how does an antimatter engine actually work? Let's break it down. There are 3 main types of conceptual designs, each slightly more terrifying than the last. First, the most basic, the direct annihilation drive. In this version, you inject tiny amounts of antimatter into a reaction chamber where it meets matter. The resulting gamma rays are converted into thrust, sometimes using specially designed reflectors or radiation funnels. This kind of drive would offer stupendous specific impulse, a measure of fuel efficiency, but it's wildly complex. Gamma rays are tricky customers. They don't like to be focused or redirected. They just zip through matter like it's not there, which makes capturing their energy a tad inconvenient. Second, the beamed core engine. This is the more sophisticated cousin. Instead of relying on the gamma rays, you focus on the charged pions, subatomic particles created as a byproduct of proton-antiproton annihilation. These pions can be steered using magnetic fields and ejected out the back of the spacecraft to create thrust. It's a lot like a particle accelerator strapped to a spaceship. Terrifying? Yes. Brilliant? Also, yes. And then there's the antimatter-catalyzed nuclear pulse propulsion design. Think of it as the love child of a nuclear bomb and a spark plug. You don't use antimatter as the main fuel source. Instead, you use it to trigger tiny nuclear explosions in a reaction chamber. The antimatter acts as the ignition for a fusion or fission reaction, giving you all the benefits of nuclear propulsion, but with better control and lower radioactive waste. One design like this, called ICAN-2, was proposed for crewed Mars missions, and it's not as far-fetched as you'd think. You float now beside a conceptual antimatter ship. Sleek, quiet, ominous. No flames, no roar, just a subtle hum as micromagnetic fields direct antimatter pellets into position. You imagine the ship pulsing forward with each controlled reaction, like a heartbeat echoing through the void. Clean, controlled, impossibly fast. But here's the delicious twist. It's not just about speed. Yes, antimatter engines could get us to Mars in weeks instead of months. They could reach the outer planets in record time, but the real magic is in delta V, the total change in velocity a ship can achieve. With traditional rockets, delta V is limited by the tyranny of fuel mass. More fuel means more weight, which means more fuel to move the fuel, and on until your payload is mostly more fuel. Antimatter skips that loop. It offers such high efficiency that your ship could carry more supplies, more shielding, more science stuff, or just go faster and farther. You choose. Of course, there's always a catch. Several, actually. First, we still don't have a reliable way to store antimatter in usable quantities. We covered this in the last section. Trap it wrong, and it annihilates on contact with the containment unit. Poof. Second, converting gamma-ray energy into usable thrust is not just hard, it's borderline heretical in engineering circles. And third, the radiation risk to any onboard crew would be considerable. Think sunburn from the inside out. Not ideal for long-term space napping. Still, researchers aren't giving up. NASA has looked at antimatter propulsion as part of its advanced concept studies. The NASA Institute for Advanced Concepts, NIAC, funded multiple proposals exploring practical uses of antimatter, not for interstellar jumps just yet, but for smaller scale missions like zipping probes to Saturn or Pluto in months instead of years. Historians still argue whether these studies were real efforts or just theoretical flexing to keep public interest alive. But the math checks out. The tech doesn't, yet. For a quirky little aside, one proposal involved storing antimatter in the form of muons, short-lived particles created in particle collisions. Muons can catalyze fusion reactions and might be easier to handle than antiprotons. Emphasis on might. They also decay in microseconds. So, time's a bit of a problem. Back in your imaginary ship, the antimatter chamber glows softly. You've made it stable. The containment works. Each antimatter reaction gives you a clean push forward. No noise, no waste. Just momentum, physics, and a quiet defiance of every limit that held us back before. You drift onward. The stars ahead no longer unreachable, but merely far. And in your wake, a trail of photons. Nothing more, nothing less. You're inside the engine room now, or what would be the engine room of a future antimatter-powered spacecraft. It doesn't look like a greasy, piston-laced mess. No dangling wrenches or coils of cable. Instead, it's eerily clean, sterile. At the centre of it all, there's a levitating chamber, a vacuum-sealed, magnetically balanced jewel of engineering. Inside, a few atoms of antimatter hover delicately, like a spiderweb made of lightning and bad decisions. Containment is everything here. Because the moment even a whisper of antimatter escapes that trap and touches matter, any matter, it's game over. Not dramatic Hollywood-style fireballs, but an instantaneous silent flash of energy that vaporizes the immediate surroundings. You wouldn't hear it, you wouldn't feel it, you just wouldn't be. Let's be clear, storing antimatter is probably the single hardest engineering challenge in the entire known universe. You can't just build a metal fuel tank and slosh the stuff in. Antimatter reacts with all matter, including metals, plastics, glass, and that lovely carbon-based flesh you're walking around in. So, the only way to contain it is to not let it touch anything at all. Enter the Penning trap and the Paul trap, two beautifully mad magnetic bottle technologies. The Penning trap uses a combination of static electric and magnetic fields to suspend charged particles in space. It's been used for decades to trap things like positrons or antiprotons in tiny, carefully balanced wells. You can imagine it like juggling charged marbles in a frictionless magnetic field, where any misstep leads to instant oblivion. The Paul trap, meanwhile, uses dynamic electric fields that oscillate rapidly to confine particles in a sort of invisible cage. It's like trying to balance a ping-pong ball in a constantly moving wind tunnel. Complicated? Yes. Effective? Sort of. Now you might be thinking, cool, just toss some antimatter in there and hit the gas. But here's the rub. These traps only work for individual particles or extremely small clouds. We're talking nanograms, maybe picograms. A single sneeze from your dog contains more mass. Scaling up to something like fuel-grade quantities, milligrams or grams, introduces problems so complex they make quantum physics look like IKEA instructions. Historians still argue whether it's even possible to scale up magnetic traps in a way that would allow for practical storage of propulsion-grade antimatter. The fields required would need to be mind-bogglingly strong and stable. The slightest deviation in charge balance, a power hiccup, or even a cosmic ray hitting a controller chip could be enough to destabilize the system. Think of it as trying to balance a bowling ball on a stack of marbles during an earthquake, while blindfolded. There's also the problem of vacuum. You can't have any atoms of regular matter floating around near the antimatter, not even a stray hydrogen molecule. So, you need near-perfect vacuum, far better than anything your average vacuum chamber can provide. These are the same conditions we find in deep space itself, which is handy, but we haven't built ships in space yet, so the whole containment system needs to survive liftoff from Earth, which adds another delightful twist. Vibrations. Rockets rattle. Traps don't like rattling. You float now alongside one theoretical solution, a series of nested magnetic coils, all stabilized by superconductors operating at cryogenic temperatures. The antimatter sits in the very center, suspended like the world's most dangerous snow globe. The system is isolated from the ship's structure. Redundant power supplies hum quietly. Every wire has a twin. Every capacitor has a cousin. It's the engineering equivalent of bubble wrapping a grenade. But even that only buys you so much. What if you want to move the antimatter, or inject it into a reaction chamber. The act of transferring antimatter, getting it from the containment unit into the engine in just the right amount at just the right moment, is like passing a blowtorch through a paper tunnel and hoping for a light breeze. Some designs propose using electrostatic accelerators to launch individual antiprotons into a fuel substrate, usually hydrogen or deuterium. These are so precisely timed and aimed, it makes a Swiss watch look like a sundial. The antimatter particle hits the target, annihilates, and the resulting burst of energy propels the ship forward. Do it again and again, thousands of times per second. And then you ask, what powers the containment? Because if your ship's batteries fail and the magnets shut down, the antimatter doesn't wait politely, it just acts. So you'd need triple redundancy, multiple generators, solar backups, maybe even nuclear batteries just to keep the field running, even during deep space sleep mode. You don't turn off an antimatter trap, you watch it while it watches you back. There's one final nightmarish twist to all of this: secondary particles. When antimatter annihilates, it doesn't just release gamma rays, it can also spit out neutrinos, charged pions, and high-energy photons that blast through materials like they're wet tissue. Your containment unit and everything near it has to be shielded, and shielded again. Otherwise, the very act of propelling your ship slowly cooks your crew from the inside out. Astronauts make terrible casseroles. For a quirky little tangent, some speculative designs involve surrounding the antimatter core with a layer of frozen matter, an ice buffer if you will, so if containment fails, the antimatter annihilates inside the ice, and the blast is absorbed before it reaches the ship's hull. Yes, someone at NASA really proposed the spacefaring equivalent of putting your bomb inside a popsicle. So you drift through this imaginary spacecraft eyeing the antimatter chamber like it's a tiger in a tutu, equal parts majestic and murdery. It doesn't roar, it doesn't glow, it just waits, perfect, silent, and profoundly indifferent to your survival. You wonder now if this is really the fuel of the future, or a power so dangerous it might never leave the lab. And that's a fair thought, because even the most stable traps we've built so far hold only micropuffs of positrons or antiprotons. We're miles away from fueling a probe, let alone a ship. But every year the traps get better, the containment lasts longer, the errors shrink, the dream inches forward, because once, just once, we do trap enough antimatter and control it precisely enough to push a spacecraft forward without killing anyone. That's the moment everything changes. You drift now through a long, quiet comparison. Two ships side by side. One is bulky, armoured, humming with radiation shields and lead-lined tanks. The other is sleek, compact and chillingly quiet. Almost too quiet, like it knows something the rest of us don't. This is the duel that's been playing out in lab proposals and whiteboard schematics for decades. Antimatter versus nuclear propulsion. One, a power source barely within our grasp. The other, a volatile friend we've known since we lit up the desert sky at Trinity in 1945. So which one wins, the old atom splitter or the antimatter whisperer? Let's line them up. Starting with the current heavyweight, nuclear propulsion. It comes in several flavours. You've got your classic nuclear thermal propulsion, NTP, where a reactor heats liquid hydrogen until it blasts out the back of your ship like a jet of angry vapour. Simple, rugged, tested. The US ran full-scale ground tests back in the 1960s under a project called NERVA, which you'll love for its Cold War optimism and total disregard for safety margins. Then there's the more exotic nuclear electric propulsion, NEP. This uses a nuclear reactor to generate electricity, which then powers ion engines. Less thrust but incredibly efficient. You can imagine it like coasting on a nuclear breeze for months, slowly building up speed. But both of these have the same Achilles heel: waste. Nuclear propulsion is powerful, but it's messy. You need shielding, you need cooling, you need a plan for the day someone cracks a coolant pipe in orbit and turns your engine room into a glow stick from hell. And then, of course, there's nuclear pulse propulsion, the wild child. Most famously proposed in Project Orion, a plan to launch a ship using a series of actual nuclear bombs detonated behind it, with a giant metal plate absorbing the shock. It's simultaneously the most ridiculous and most genius thing we've ever thought of. It works, in theory. But international treaties and basic human sanity have kept us from testing it. Now, slide your attention back to antimatter. It has no waste, no melted uranium rods, No radiation left behind, at least not in the traditional sense. When antimatter annihilates matter, it's all gone. The reaction is complete, clean, efficient, brutally elegant. In raw power terms, antimatter makes nuclear look like a sparkler at a fireworks show. 1 gram of antimatter reacting with 1 gram of matter releases more energy than a multi-megaton nuclear warhead. You can't get better than 100% mass-to-energy conversion, and antimatter gives you that. Every single time. But here's where nuclear propulsion fights back. Availability. We already have uranium. We already have reactors. We know how to build containment systems. We've launched radioactive payloads into space before. RTGs, the power sources behind the Voyager probes and Mars rovers. Nuclear has a well-worn playbook. Antimatter? Not so much. Remember from earlier, we produce nanograms per year. If you filled a teaspoon with antimatter today, it would represent hundreds of millions of years of current production. Also, nuclear propulsion doesn't care if you bump into a wall. If your antimatter containment fails, you don't just get a mess, you get vaporized. But let's get back to performance, because that's where the antimatter engine starts sharpening its claws. The metric of choice here is specific impulse, ISP, which tells you how efficiently a propulsion system uses its fuel. Chemical rockets sit around 450 seconds. Nuclear thermal systems? About 900 seconds. Antimatter engines? Theoretically up to 10 million seconds depending on the setup. That's not a typo. It's a leap so vast the scales barely overlap. With that kind of efficiency, you could reach Mars in 30 days, Pluto in a few months, Alpha Centauri in a few decades, assuming we master long-duration life support, shielding, and the minor challenge of not disintegrating when we hit interstellar dust. But not everything's numbers and physics. Let's talk reliability. Nuclear systems can be turned off, cooled down, even repaired, if you've got the right tools and some nerves of steel. Antimatter containment? It's not forgiving. It's not patient. It has no off switch. The traps need to work perfectly, continuously, forever. Any failure, and the reaction isn't a slow meltdown. It's an instantaneous, catastrophic event. Historians still argue whether this intrinsic danger will forever limit antimatter engines to unmanned probes, leaving the crewed missions to the tried-and-true reliability of nuclear. It's a fair debate. You can shield against neutron radiation, but you can't shield against absolute annihilation. For a fun and slightly terrifying aside, there's an old speculative plan from the early 2000s that proposed combining the two technologies. You'd use antimatter to trigger fusion reactions, a kind of catalytic approach that would give you the thrust of fusion with less fuel mass. It was pitched as a way to avoid using entire city-sized reactors. It also meant your ship was carrying both nuclear material and antimatter. So, very relaxing. But here's where we land. Nuclear propulsion is the bridge, the thing we can do today. It gets us back to the Moon, then Mars, maybe the outer planets. We're already building the first flight-ready NTP systems for test missions in the 2030s. Antimatter propulsion is the horizon, the thing we dream of when we think beyond our solar system, not just to get there faster, but to make the journey itself plausible. You float now between the two ships again. The nuclear one hums like a diesel generator, strong, reliable, grumpy. The antimatter one? It glows faintly. You can't even hear it. It just is. A whisper of pure potential, held in place by engineering miracles and faith. And as always, it comes down to one question. Do we play it safe, or do we chase the perfect flame? You hover now in a pristine white laboratory, not one from the future, but very much the present. In one corner, a chilled vacuum chamber hums faintly. Nearby, a scientist stares lovingly at a screen displaying a readout so precise it includes decimal points of nanograms. Welcome to the unglamorous side of antimatter, the supply problem. Because here's the hard truth. If antimatter is the fuel of the future, then right now, we're about as close to powering starships as a campfire is to running a supercomputer. Let's talk about the economics of dreams, specifically how impossible it currently is to gather even the tiniest usable amount of antimatter. First off, antimatter isn't something you mine or find under rocks. It doesn't occur naturally on Earth in harvestable quantities. Instead, we manufacture it, painfully, expensively, and inefficiently, inside particle accelerators. The current world leader? CERN, of course, with help from other facilities like Fermilab and Brookhaven. All of them can produce antimatter, but they do so as a side effect of high-energy particle collisions, not with any industrial-scale intent. Picture this. You slam protons into a metal target at near-light speed. In the resulting chaos of exploding quarks and shrapnel physics, you get a shower of particles, including some antiprotons. These are magnetically separated, slowed, trapped, and then stored if they don't annihilate themselves first. It's like trying to catch feathers with chopsticks while standing in a wind tunnel, wearing mittens. How many antiprotons can you catch this way? Not many. The total global production of antimatter each year is measured in nanograms. To put that into perspective, 1 nanogram is about 1/1000th of a gram. And even that takes megawatts of energy and millions of dollars to achieve. So let's dream for a moment. Suppose we wanted to fuel a small deep space probe using just 1 gram of antimatter. That single gram would cost, ready for this, somewhere between $62 trillion and $100 trillion using current production methods. That's more than the entire GDP of most countries, just to fill your cosmic gas tank. No snacks, no bathroom breaks, just fuel. And even if you had the money, you'd still be stuck waiting for a few thousand years to produce enough, unless production technology advances dramatically. Still, researchers aren't giving up. There are ongoing efforts to reduce the cost and increase the yield. Some scientists are developing more efficient target materials to increase the number of antimatter particles produced per collision. Others are working on better capture methods, reducing how many particles escape before they can be stored. The Holy Grail, a system that could mass-produce antiprotons at gram scale per year, not per eon. Historians still argue whether the lack of funding for antimatter production is because of its impracticality, or if its potential applications, especially military, are being pursued behind closed doors. Fringe theorists love to speculate about black budgets and secret propulsion tests. No public proof, of course, but it's oddly comforting to imagine somewhere in a bunker there's a tank holding a full milligram of antimatter like a glowing, purring cat. For a fun and slightly absurd example, in 2006, NASA's Institute for Advanced Concepts proposed a small antimatter engine that could be powered by just 10 nanograms of positrons. The idea was to use it not for crewed missions, but to launch microprobes to the outer planets. These would be fast, light, and relatively cheap if you could make the antimatter. Spoiler alert, we still can't. But the fact that the design was even mathematically viable says something. And here's a quirky side note. Hospitals produce antimatter every day. Yup, medical antimatter. In positron emission tomography, PET scans, hospitals use short-lived radioactive isotopes that emit positrons. Those positrons, in turn, annihilate with electrons in your body, producing gamma rays that are detected and turned into 3D images of your insides. So the next time you get a scan, you can say you're powered by antimatter briefly. Of course, PET scanners only use tiny amounts, but still, proof that antimatter can be produced and used safely in the real world, just not for rocket fuel, yet. You float now beside a hypothetical antimatter refinery. Pure speculation, of course. It sits in orbit, collecting solar power and feeding an onboard accelerator. It creates antiprotons slowly, carefully, and stores them using ultra-cooled magnetic traps. Over years, it builds a microcache of fuel, enough for a tiny propulsion system or a high-energy experiment. These antimatter farms are one of the only plausible paths forward, removing Earth's gravity and atmosphere from the equation and using the sun's energy for the enormous input power required. But the real future lies in breakthroughs we haven't made yet. Maybe a new form of collisionless plasma that generates antimatter in bulk. Maybe a quantum loophole in how we store antiparticles. Maybe we find natural sources of antimatter in space, like those around pulsars or black hole jets, and harvest it there instead of making it ourselves. More on that later. For now, we work with what we have, and that means grams are dreams. We build engines, run simulations, and write white papers based on amounts of fuel that could literally fit on the head of a pin. Entire propulsion concepts exist for spacecraft powered by nanograms of antimatter, because we've accepted that this stuff is precious. Wildly, cosmically precious. So the next time you hear someone say antimatter propulsion is just around the corner, smile politely. Because until we can build the antimatter equivalent of a gas station, those drives will remain parked in the future. And yet, here you are, still floating, still dreaming. Because even with these absurd costs, Even with these laughable yields, the physics is real, the math checks out, the promise is unshaken. One day, you may hold in your hand the rarest, most potent drop of fuel ever made, just don't drop it. Now you're floating through the blueprints of imagination, sketches half finished, engines scribbled in margins, equations surrounding rough outlines of ships that don't exist yet, but absolutely should. These are the wild children of theoretical physics, the antimatter-powered spacecraft designs that have danced through academic journals, NASA PowerPoints, and the dreams of bold engineers who apparently never learned the word impossible. Welcome to the speculative shipyard, where we explore concepts like Project Valkyrie, AIM-STAR, and even that one propulsion idea that casually tosses around black holes like they're AAA batteries. Let's start with Project Valkyrie, a name that already sounds like it belongs in a 1990s sci-fi video game. Conceived by physicist Dr. Charles Pellegrino and others, Valkyrie is a spacecraft designed to reach 12% the speed of light. Not warp speed, but still fast enough to cross interstellar space in decades rather than centuries. The idea? Use antimatter as a trigger, not the main fuel source. In Valkyrie, tiny pellets of nuclear fusion fuel, deuterium and helium-3, are compressed and ignited by micrograms of antimatter. The resulting fusion reactions blast out high-energy plasma, which is magnetically directed out the back of the ship. Repeat this process millions of times and you get a smooth, continuous thrust. No boom, no chaos, just a heartbeat of controlled microfusion detonations. Now you might ask, why not just use fusion alone? Well, here's the rub. Fusion is notoriously hard to start. It takes extreme pressure and heat. But a pinprick of antimatter touching matter? That'll do it. It's like lighting a campfire with a lightning bolt. Terrifying, yes, but very effective. Project Valkyrie never left the whiteboard, of course, but it's one of the most plausible ideas we've had for interstellar antimatter propulsion. It cleverly sidesteps the "we don't have enough antimatter" problem by using it only as a trigger, not as the primary fuel. Milligrams, not grams. A spoonful of doomsday instead of a truckload. Next on the tour, AIM-STAR, short for Antimatter-Initiated Microfusion Starship. Also a real proposal. AIM-STAR takes the Valkyrie idea and miniaturizes it. Imagine a ship the size of a small building, packed with ultra-precise particle injectors and a long magnetic nozzle. Again, it uses tiny doses of antimatter to start fusion in small capsules of fuel. The advantage? Compact size. This ship wouldn't carry astronauts. It would be an uncrewed interstellar probe, capable of reaching a nearby star system in a human lifetime. AIM-STAR even has theoretical paths for slowing down once it gets there. Because remember, going fast in space is easy. Stopping? That's where things get spicy. AIM-STAR would use a reverse thrust system involving its own magnetic field in the interstellar medium, a bit like deploying a parachute made of magnets to slow down against cosmic dust. Science says, maybe. Engineers say, not yet. And just when you think these designs are bold, here comes the fringe superstar. The black hole drive. Yup, you heard that right. This one's been whispered about in physics circles and occasionally shouted on late-night YouTube channels. The Kugelblitz engine. The core idea is to create a tiny, artificially generated black hole using a focused beam of light, or theoretically a massive blast of antimatter-induced gamma radiation. The black hole would then emit Hawking radiation as it evaporates, and this radiation could be harnessed as thrust. Think of it like holding a baby sun in a cage and letting it scream you across the galaxy. Is it realistic? Number. We can't make black holes. We don't even know if Hawking radiation exists for sure, but on paper, the numbers add up. A Kugelblitz drive fueled by antimatter-generated gamma burst could, in theory, accelerate a ship to a significant fraction of light speed. Just don't drop the containment field. Back to Earth for a second. These concepts all have one thing in common. They assume we'll eventually master microgram-level control of antimatter. Not just making it, but storing it, moving it, and triggering reactions with surgical precision. That's a level of technological maturity we are nowhere near. Yet. Historians still argue whether projects like Valkyrie and AIM-STAR were genuine prototypes, or just thought experiments designed to explore the limits of known physics. Some say they were Hail Mary passes thrown across the void of engineering. Others argue they were never meant to fly, just to inspire, a push for funding, a dare to future generations. For a quirky interlude, In the late 1980s, a small aerospace company proposed a spacecraft concept called Firefly. It wasn't related to the TV show, though it certainly would have fit in. Firefly would carry a payload of just a few nanograms of antimatter, using it to vaporize thin foil sheets of conventional fuel. The sudden burst of energy would push the ship forward in ultra-precise pulses, like rowing through space with a laser-tipped oar. It never got beyond the proposal stage, but the physics wasn't wrong, just wildly impractical. Still, someone wrote the funding request. That counts for something. You drift now above a dry erase board covered in designs, all variations on a dream, that we can build engines not with brute force but with elegance, with annihilation, with precision. These ships won't run on fire, they'll run on thought, on the sharp edge between what we know and what we dare to attempt. The future of spaceflight might not look like rockets at all. It might be whisper quiet, a gentle flicker of charged particles, a breath of antimatter igniting fusion behind you, a push so perfect, so silent, that the only thing you hear is the creak of your chair as you look out the window and realize Earth is already a pale dot behind you. The best part? Every one of these ideas is waiting, in notebooks, in labs, in simulations. The blueprints are ready, the physics is sound. All we need is time, and of course, a few $1 billion worth of antimatter. You're holding it now. A spoonful of impossibility. Suspended in mid-air, held in place by invisible fields and 1,000 layers of fail-safes, is one shimmering drop of antimatter. It doesn't glow, doesn't hum, doesn't look dangerous. But you know better. It's less than a gram, but in your hand you cradle the potential energy of an extinction-level event. This is the point in the bedtime story where your pillow gets a little tenser. Let's walk through the numbers, because sometimes math is the best horror story. A single gram of antimatter, when combined with a gram of regular matter, releases around 1.8 times 10 to the 14th power joules of energy. That's 180 trillion joules. For comparison, the Tsar Bomba, the most powerful nuclear weapon ever detonated, released 210 petajoules. So your spoonful of doom is roughly 85% of the largest bomb humanity has ever made, in something smaller than a sugar cube. Let's say you were to drop that spoonful, assuming it wasn't stored inside a precision magnetic trap in a high vacuum and surrounded by enough shielding to block a small sun. The instant it touched air or a bit of dust or your sleeve, annihilation would occur. The entire spoonful would vanish in a white-hot burst of gamma rays and high-energy particles. The result? The equivalent of a 43 kiloton nuclear blast with none of the radioactive fallout. Just pure energy, silent, instantaneous, efficient in the most terrifying sense of the word. No wonder antimatter is sometimes called the perfect weapon. And yes, military groups around the world have noticed. In fact, various declassified documents from the Cold War era mention the theoretical use of antimatter as a trigger for nuclear weapons, or even as a potential energy source for small tactical explosions. No such weapon is known to have been built, but the idea was tempting. If you could create just a microgram of antimatter, you wouldn't need complex triggering systems for thermonuclear warheads. One pinprick of annihilation would do the job. Still, even those secretive agencies ran into the same problem: cost and containment. Micrograms of antimatter cost more than the entire global defense budget, and storing it safely is like building a house of cards in a wind tunnel made of explosives. Back to our spoon, still suspended mid-air. You can't help but appreciate the poetic elegance of it. Antimatter doesn't hate you. It doesn't want to explode. It just is, a perfect counterpart to everything we are. But its very existence, in our matter-based universe, is incompatible with safety. There's no margin of error, no leeway, no second chances. That's why any future spacecraft carrying even milligrams of antimatter will treat it not just as fuel, but as a live payload. The entire ship will be designed around the containment. Layers of magnetic shielding, isolated systems, multiple power backups, an entire department of people whose full-time job is to make sure the antimatter doesn't so much as notice the ship exists. And still, accidents happen, which is why some researchers have proposed a clever workaround. Don't store it at all. Produce it on demand. It's a bold idea. Use compact accelerators or other exotic methods to generate tiny bursts of antimatter exactly when needed. You inject those bursts into your propulsion system, get a clean push, and repeat. No storage risk, no spoonfuls of doom, just a steady heartbeat of micro-annihilations. Unfortunately, that comes with its own set of problems. Generating antimatter on the fly requires staggering amounts of energy, extreme precision, and, most critically, a system that won't vaporize itself in the process. But it's not impossible, just wildly ambitious. Historians still argue whether the idea of a spoonful of doom has held back real progress in antimatter research. The word alone, annihilation, tends to make grant committees nervous. But that's the thing. Antimatter isn't evil, it's just physics. The real issue isn't the danger, it's our lack of control. We don't fear the matches, we fear what happens when the matchbook catches fire in our back pocket. For a more playful aside, did you know that the Star Trek universe has quietly shaped much of our public understanding of antimatter? The warp drives on the Enterprise run on matter-antimatter reactions, controlled by something called a dilithium crystal, which amusingly is not a real thing. Still, the basic idea was surprisingly accurate. Contain antimatter, mix it carefully with matter, harness the energy. If you ignore the fictional geology and glowing control panels, it's not far off from modern propulsion concepts. But unlike Star Trek, we can't just beam the antimatter into a reaction chamber and shout engage. We need careful staging, feedback loops, and the kind of redundancy normally reserved for nuclear submarines and emergency room defibrillators. And yet, the dream persists. You imagine now a ship cruising at 10% the speed of light, powered by controlled microbursts of annihilation. Each gram of antimatter bought, built or harvested represents months of thrust. You don't burn it, you spend it, atom by atom, like the universe's most expensive currency. And maybe, just maybe, that spoonful of doom becomes a ticket out of the solar system. A way to leave behind the gravity wells and orbital limitations and coast into the deep dark. Still, you can't shake the awe. That something so small, so precise, so quiet, could contain such staggering power, not in the form of fire, not in the sound of engines or the rumble of rockets, but in a silent kiss between two particles who were never meant to meet. That's antimatter, the deadliest whisper in the universe. Now, you're aboard the ship. Not a dream, not a sketch, not a chalkboard of maybe. You're really here. The humming is gentle, the cabin light's low, and there's a rhythm in the deck under your feet. Not quite vibration, but the feeling of momentum. A subtle pulse that tells you this thing is moving. Not like a plane, not like a rocket, but really moving. At this speed, Earth is shrinking behind you like an old photograph curling at the edges. You're on your way to Mars, and the fuel, just a few flecks of antimatter, barely enough to coat your fingernail. This is the antimatter-powered Mars trip, the hypothetical one engineers daydream about between grant applications. It's not fiction. It's a plausible path, assuming we solve a few dozen colossal engineering challenges and one or two economic ones like, oh, the cost of producing and storing antimatter at scale without triggering bankruptcy or vaporization. Still, let's imagine we did it. Imagine you're one of the first astronauts not riding a chemical rocket or a nuclear engine, but something new. Your ship doesn't roar off the launch pad in a pillar of fire. Instead, it assembles in orbit, likely launched in segments and built piece by piece. No need to carry volatile antimatter through the atmosphere. Once complete, the fuel is added last, with robotic precision and the nervous caution of someone handing over an armed grenade made of diamonds. The engine is a beamed core antimatter propulsion system, the kind we teased back in Section 4. It uses stored antiprotons and carefully engineered collisions with hydrogen or deuterium. The annihilation reactions produce charged pions, and those pions are steered out the back of the ship using magnetic nozzles, creating thrust. You don't feel a jolt. There's no sudden burst, just a constant gentle push, like drifting downstream on a perfectly still river. But in space, that push adds up fast. A traditional chemical mission to Mars takes around 6 to 9 months, depending on launch windows and orbital geometry. An antimatter-powered ship? 30 to 45 days, depending on your thrust level and trajectory planning. Fast enough that you don't need to wait for the perfect alignment of planets. Just go. What do you do with all that extra time? Well, for one, you dramatically reduce the crew's exposure to cosmic radiation, which becomes a serious concern in long-term missions beyond Earth's magnetic shield. On a 9-month trip, radiation doses accumulate to dangerous levels. Unless you're packing half your mass in shielding, which adds weight and cost. But in a 30-day sprint, the exposure is manageable, less shielding, less cargo, faster arrival. Antimatter, 1. Radiation, 0. Second, you minimize the effects of microgravity. Spend months floating weightless, and your body forgets what bones are for. You lose muscle mass, calcium, balance, and your sense of humor. That's why most Mars mission plans include spin gravity, or treadmill straps and twice-daily pep talks. But in 30 days, you're just uncomfortable, not deteriorating. Still, it's not all perfection and anti-elegance. Let's peek into the complications. First, you have to slow down when you get there. High thrust is great for leaving Earth, but what happens when Mars is rushing toward you at tens of thousands of kilometers per hour? You need a plan for deceleration. That means either carrying extra antimatter to reverse thrust into orbit, doubling fuel needs, aerobraking in the Martian atmosphere, which is thin, tricky and bad news if you overshoot, or using a staged propulsion system, like coupling the antimatter engine with a more traditional system for the final approach. Second, there's the very real issue of engine efficiency. Even the best antimatter designs suffer from gamma-ray waste. That is, a big portion of the annihilation energy turns into gamma rays that you can't easily direct as thrust. These rays need to be absorbed or deflected, and they tend to pass through just about everything, including you. So your ship is going to have a massive radiation shield, likely a heavy chunk of tungsten or lithium hydride sitting between the engine and your crew habitat. And here's where the design starts looking awkward. You've got the crew capsule on one end, the fuel tanks spaced out like nervous siblings, the antimatter containment far away and surrounded by a spider's nest of magnetic coils, and the radiation shield sandwiched in between. The whole ship looks less like a sleek rocket and more like a very anxious centipede. But it works, at least in theory. And while you coast at a fraction of a light speed toward the red planet, you have time to think about how far we've come, about how many decades we spent throwing things into space using exploding firewater like medieval alchemists with dreams of flight. Historians still argue whether this kind of antimatter Mars ship will ever be built, or whether it's just too dangerous, too expensive, too optimistic. After all, we haven't even set foot on Mars with any propulsion system. But those same debates once surrounded nuclear engines, reusable rockets, and even flight itself. Besides, there's something elegant in knowing that a mission to another planet could be powered by annihilation, by precision, by quiet physics instead of thunder. For a quirky side note, a 2004 NASA-funded study explored the idea of hybrid engines for Mars trips, using a small amount of antimatter to initiate fusion reactions for thrust. These antimatter-catalyzed microfusion engines would need just a few micrograms of antiprotons to shorten the trip to Mars dramatically. The catch? Even producing those micrograms would require the full attention of the world's largest particle accelerators for years. Still, you can't help but imagine. You peer out the viewport. Mars is growing larger now, a crimson disk swelling against the black. The engine is quiet. The ship is smooth. And somewhere, deep inside the magnetic trap at the rear of the ship, a few millionths of a gram of antimatter is doing the work of 1,000 tons of rocket fuel. It's not just science fiction anymore, it's just future. And you? You're not just a passenger, you're part of the first wave, riding to Mars on a beam of annihilation. You're not really moving now, at least not in a way your body can feel. No rumble, no shake, no G-forces squishing your organs against your spine. Just a persistent low hum in the ship's systems, and the subtle knowledge that the stars ahead are shifting very slowly ever so slightly as your velocity climbs. This is what it feels like to brush against relativistic speed, the domain of time dilation, the place where physics starts stretching reality like taffy. You're not just heading to Mars anymore, you're thinking bigger, faster, stranger. You want to ride that antimatter engine until the stars start to warp and time itself starts giving you side-eye. Let's talk about what happens when you go really fast, close to the speed of light, and how antimatter propulsion might actually get us there. First, a quick refresh from your high school nightmares. According to Einstein's theory of special relativity, as an object approaches the speed of light, its mass effectively increases. It takes more and more energy to push it just a little bit faster. At light speed, you'd need infinite energy, which is, let's face it, a bit much, even for antimatter. but antimatter propulsion could get us to a healthy percentage of light speed. Say, 10% to 30% of c, where c is the speed of light, roughly 300,000 kilometers per second. That's still impossibly fast by today's standards, but within the mathematical reach of beamed core or antimatter catalyzed engines. At 10% of c, you could reach Proxima Centauri, our closest neighbouring star system, in just over 40 years. Not bad, long vacation, but doable. At 50% of c, the trip shrinks to 9 years. And here's where things start to get spicy. At those speeds, time dilation kicks in. What does that mean? From your point of view, time aboard your ship would slow down relative to observers back on Earth. At 90% of the speed of light, every day you experience might be 2 days for someone on Earth. At 99.9% of c, you could cross light years in what feels like months or weeks to you, while decades or even centuries pass back home. You don't feel the change. There's no alarm that rings when your clock goes out of sync with Earth's, but slowly, invisibly, your ship becomes a pocket of slow time, gliding through the cosmos. Your family would age, governments would change. Maybe Earth wouldn't even be recognizable when you came back, if you came back. Some scientists refer to this as the time travel paradox of deep space propulsion. You don't travel through time like a DeLorean hitting 88 miles per hour. You just skip ahead, riding the relativistic curve like a surfer cutting across the edge of a wave. Historians still argue whether the effects of time dilation are a feature or a bug in human space travel. On one hand, it makes multi-decade voyages tolerable for the crew. On the other, it guarantees disconnect from Earth, from loved ones, from history. It's a one-way trip to the future. For an eerie twist, imagine being one of the first interstellar travelers. You leave Earth in 2100. You travel at 99.99% the speed of light. You reach your destination, say Tau Ceti, in 10 subjective years. You land, step out, plant a flag, and then check the calendar. It's the year 2450 back on Earth. Everyone you know? Gone. Languages changed, borders erased, AI presidents and floating cities, or maybe nothing. No reply to your hails, no blue planet on the return scan. Maybe we didn't make it, or maybe we just stopped waiting. That's the emotional cost of relativistic travel. Now back to your antimatter engine. Can it get us there? In theory, yes. The annihilation of matter and antimatter provides the highest energy per mass conversion of any known process. If you want to accelerate a ship to 10% or more of light speed without hauling a gas station behind you, antimatter is your best bet. The challenge isn't just the fuel, it's how to keep the crew alive during that acceleration. You can't slam into relativistic speed like a fighter jet. You need gradual thrust, days or weeks of consistent, gentle acceleration, building speed over time until the stars start to blur. And then there's deceleration. Because what's the point of reaching another star system if you whiz past it in a single, awkward oops? You'll need just as much fuel, or clever braking systems using magnetic sails or interstellar drag, to slow down safely. There's even an entire theoretical engine designed for this, the Bussard ramjet, which scoops hydrogen from space and uses it for fuel along the way. If paired with antimatter, you get a hybrid system that might be able to refuel mid-flight. The science is hazy. The dreams are vivid. For a slightly absurd aside, if you reach speeds above 99.999999% of light, time on your ship would practically stop relative to Earth. You could, in theory, reach the edge of the observable universe in what feels like minutes. But let's not get greedy. Physics still wants to be invited to the party. You're drifting again now, not through space, but through thought. A ship like this, an antimatter-powered relativistic time capsule, doesn't just challenge engineering, it challenges identity. What do you become when the universe ages without you? What happens when you come home and find it's not your home anymore? Would you go, knowing you'd return to a world of strangers? Or maybe you don't come back at all. Maybe you find something else, some new world, some untouched system, and decide to start over. To become the seed of something new. That's the real promise of antimatter propulsion. Not just speed, but possibility. The power to unstick us from time, to float between centuries, to say, we were here, we left, and we found something more. And right now, you're still coasting. Mars is far behind, the stars are ahead. And somewhere inside the engine, a few atoms vanish in perfect annihilation, pushing you closer to the future. You've been drifting in peace, in silence, in the long hush of relativistic thought, and now you tilt slightly, peering down through the window of speculation into a darker current running beneath the antimatter dream. Because for every hopeful propulsion schematic, for every whisper of Mars trips and interstellar rides, there's another set of documents, shrouded in red tape, stashed in safes, stamped classified. This is the other side of antimatter, military fantasies and forbidden tech. The engine that could take you to the stars, it could just as easily be aimed at a city. A lab breakthrough that propels a probe to Saturn in weeks. It could also be a suitcase bomb if you're willing to break a few international treaties and every moral compass within reach. So let's walk the quiet corridors of history, where antimatter wasn't seen as a miracle fuel, but as a potential superweapon. One that makes nukes look clumsy and outdated. Let's start with the Cold War, because of course we do. In the 1980s, at the height of military paranoia and technological one-upmanship, a few researchers at Los Alamos National Laboratory began looking into the potential of antimatter, not for propulsion, but as a trigger. The idea was clever in its horrifying simplicity. You don't need conventional explosives to start a nuclear reaction if you can deliver annihilation energy in a precise microscopic burst. Just a pinch of antiprotons, less than a microgram, would be enough to start fusion reactions without the massive infrastructure of a fission bomb. Suddenly, nuclear warheads become smaller, lighter, more efficient, and terrifyingly portable. You wouldn't need a city-sized missile silo, just a backpack, a briefcase, a drone. These proposals never made it out of the concept stage, or so we're told. Funding was denied, containment was too risky, the costs too high, but the physics? Still valid. Historians still argue whether this was a real weapons race or just a bluff, designed to spook the other side into wasting money. Some argue that antimatter weapon concepts were deliberately inflated. Disinformation, science fiction masquerading as strategy. Others insist the work was real, ongoing, and perhaps never entirely shut down. But even if no weapon was built, the dual-use nature of antimatter research hasn't gone unnoticed. That same containment field meant to cradle fuel for your Mars ship, it could just as easily be used to hold a microgram of antimatter for military deployment. The same beam injector that carefully delivers antiprotons into a fusion chamber. It could be used to fire them into a warhead, bypassing safety checks and launch codes. Antimatter doesn't play favourites, it obeys physics, not politics. And so, modern antimatter research has to walk a tightrope. It's no accident that many papers, experiments and designs focus on propulsion, not power. Funding for antimatter often arrives with a wink and a disclaimer, peaceful applications only. But every physicist working with it knows the truth. There's no firewall between engines and weapons. It's all a matter of containment and intent. Now let's dip into the weirder side, the speculative reports, the conspiracy theories. Some documents from the early 2000s suggest that the US Department of Defense commissioned studies on antimatter-fueled directed energy weapons. Imagine a beam of gamma rays generated by tiny annihilation events focused into a single line of destruction. Death rays, basically. Star Wars, but without the crawl. Other fringe rumours swirl around spy satellites powered by positron decay, or deep space surveillance drones that never run out of fuel. Even whispers of antimatter mines buried on moons or asteroids, ready to be detonated from afar. No evidence, of course, just enough math to make the dreams possible, and just enough secrecy to make them believable. For a bizarre side note, in 2004 there was a brief media storm after a report claimed that NASA had developed a positron weapon. The reality? It was a misinterpreted science proposal for antimatter propulsion. But for a week or two it was all over the headlines. NASA building gamma ray bombs. Headlines never change. So where does that leave us? In a precarious place, honestly. Because even if we solved the production problem, even if we could manufacture antimatter at scale, store it safely, and use it cleanly, who gets to use it? And how do we keep it safe? Unlike nuclear weapons, which require complex refinement and rare isotopes, antimatter is universal. If you have the right tech and enough funding, you can make it, contain it, use it. There's no radioactive fingerprint, no long half-life, just energy. That makes it the ideal weapon. Clean, deniable, instantly destructive, and difficult to trace. Which is why most scientists today are, shall we say, very careful with how they describe antimatter applications. They emphasize scientific potential, space travel, medical imaging, deep space probes, all the fun, inspiring stuff, the words weapon, trigger, and detonation get edited out in peer review, or more commonly, never make it into the paper in the first place. But make no mistake, the knowledge is there. And if we ever cross the threshold, if containment tech matures and antimatter becomes less rare than moon rocks, someone will weaponize it. It's not a question of if, only when. You glance now at the antimatter trap on your ship, the one built for propulsion, for peace, and for a moment, you imagine it mounted in a missile, or dropped from orbit, or lost in a diplomatic crisis. A single gram, enough to erase a city. The same particle that could carry us to the stars could also end the conversation forever. So we keep it in check. We watch the labs. We fund the dream, cautiously. We build the future, one containment field at a time. Because even in the silence of space, power whispers, and antimatter, it's the loudest whisper of all. Now you're far beyond Earth, beyond Mars, beyond even the frosty realm of Pluto, drifting in a region where sunlight becomes a theory more than a sensation. Out here, in the quiet dark between stars, you find yourself thinking like a prospector. Because if we're going to power the future of interstellar travel with antimatter, we need more of it, a lot more. And that raises the question, what if we didn't have to make antimatter? What if we could mine it? Welcome to the deep space gold rush, where instead of pickaxes and tin pans you use magnetic fields and particle traps to harvest natural antimatter from the universe itself. Sounds like a sci-fi fever dream, right? And yet, some of the most legitimate physics minds alive today are seriously considering this possibility. Hey, let's start with a quiet little corner of our own solar system, Earth's magnetosphere. Turns out, Earth is already sitting in a loose antimatter hammock. When high-energy cosmic rays slam into the upper atmosphere, they generate antiparticles, mostly positrons and a few rare antiprotons. Many of these particles are swept up by the planet's magnetic field and get trapped, forming a toroidal belt around the Earth not unlike the Van Allen radiation belts. We call this the Sturmer belt, and while it's not exactly brimming with fuel, it's enough to get scientists curious. In fact, in 2011, the Pamela satellite, an Italian mission dedicated to studying cosmic radiation, detected several dozen trapped antiprotons in low Earth orbit. Not a jackpot, but a proof of concept. Nature makes antimatter, and space can store it. So now imagine orbiting collectors, like big magnetic scoops, that could sweep through these belts, gradually accumulating antimatter particles. One proposal suggested a spacecraft could, over a year or two, harvest micrograms of antimatter just by cruising through the right regions of space. It's the cosmic equivalent of panning for gold dust in a glacier stream. Still, micrograms won't power interstellar drives, so we look further. Enter the gas giants, especially Jupiter and Saturn. Both of these planetary behemoths have intense radiation belts, far stronger than Earth's, and they trap significantly higher concentrations of antiparticles. Jupiter, in particular, is a cosmic particle accelerator. Its massive magnetic field can wrangle electrons and protons at energies high enough to produce secondary antiparticles. It's like nature's own antimatter factory, running 24/7 with a budget of $0 and no health and safety regulations. Imagine placing automated harvesters in orbit around Jupiter, satellites equipped with finely tuned electromagnetic nets, slowly grazing the planet's belts for positrons and antiprotons. The idea sounds absurd, until you realize we've already done things almost as weird. We've parked probes around asteroids, we've flown helicopters on Mars, a long-term orbital antimatter harvester, that's just the next upgrade. Historians still argue whether these concepts are real roadmaps or just cosmic wishful thinking. Some say it's a clever way to keep interest alive in antimatter propulsion. Others insist that the physics is sound and that future missions could piggyback harvesting tech on top of existing exploratory spacecraft. But even that's just the start. You tilt now toward the outer cosmos, toward the more extreme environments where antimatter isn't a trickle, but a torrent. Around pulsars, spinning neutron stars with immense magnetic fields, scientists believe that natural pair production happens all the time. These ultra-dense stars emit beams of electromagnetic radiation so intense that they literally rip virtual particles out of the vacuum. Some of those particles are antimatter. Swarms of positrons and electrons race away from the star in tightly collimated jets, forming radiation storms that defy imagination. Now, obviously, parking a ship near a pulsar to collect antimatter is Let's say inadvisable. But understanding these environments helps refine our models of how and where antimatter might concentrate in the galaxy. Maybe, just maybe, there are safer eddies, dead zones, reservoirs of trapped particles drifting in the wake of ancient stellar corpses. In fact, some researchers have proposed the idea of natural antimatter clouds, regions of interstellar space where conditions were just right to separate matter and antimatter after the Big Bang. These clouds, if they exist, would be unimaginably dangerous to fly through, but also unimaginably valuable. Harvesting antimatter from such a cloud would be the ultimate score. The California gold rush, except floating in a gamma-ray soup with no rescue teams and a zero-mistake policy. For a quirky detour, there's a proposal nicknamed the Antimatter Trawler, a slow-moving spacecraft with a gigantic looped magnetic net. Think of it like a high-tech butterfly catcher. It would pass through regions rich in cosmic rays or near gas giants, slowly building up a reservoir of antimatter particles over years or even decades. The trawler wouldn't move fast, it wouldn't go far, but eventually it would return to Earth orbit with its precious cargo. And the fuel? Free. You just had to wait, and hope nothing touched the sides. Of course, this assumes we solve the storage problem. Collecting antimatter is meaningless unless you can trap it long term. That means onboard containment, possibly cryogenically cooled, redundantly powered, and surrounded by enough sensors to make a nervous system blush. You imagine such a craft now floating in the dark. No crew, no windows, just a single red status light on a black hull. Inside, a soft hum, the quiet pulse of antimatter being shepherded into traps, sorted, stabilized, and archived. Not a ship, really, more like a fuel bank. The first one of its kind. Someday those banks might orbit every major planet. Fleets of robotic collectors buzzing through radiation belts, bringing home the most potent power source ever created. Not drilled, not refined, just harvested, like rain. It's still science fiction for now, but no longer absurd. The groundwork has been laid. We've detected the particles, we've built the traps, we've drawn the maps, and all the universe is doing is waiting. Because when we finally go interstellar, we'll need more than engines. We'll need resources, logistics, infrastructure, a whole antimatter economy, and it won't start on Earth. It'll start out here, on the edge of sunlight, where the real gold rush is just beginning. You've drifted far now, not just in space, but in thought. Past the engines, the containment fields, the orbiting trawlers and Mars-bound dreams. Now you're brushing up against something stranger. Not the fringe of physics, but the fringe of belief. Because the more we learn about antimatter, the more it starts to raise a very awkward question. If antimatter exists, and we know it does, then where's the rest of it? Welcome to the world of the anti-star conspiracy. It begins with a basic symmetry. According to the standard model of particle physics and our best understanding of the early universe, the Big Bang should have produced equal amounts of matter and antimatter. Perfect balance, yin and yang. Protons and antiprotons paired off in an immaculate waltz of cosmic twins. But clearly something went wrong, or very, very right, depending on your perspective. Because everything you see, stars, gas, planets, you, is made of matter. There's no obvious antimatter, not in bulk, not anywhere we've looked. And the question is, why? Historians still argue whether this matter-antimatter asymmetry is the single biggest unsolved problem in cosmology, or just a misunderstood accounting error baked into our models. Either way, it's the elephant in the quantum room, and that's where the fringe ideas start to crawl in. What if some say there are entire antimatter galaxies out there? Not just clouds or stray particles, but fully formed, long-lived structures made of anti-stars, anti-planets, even anti-life. They wouldn't look any different from here. A hydrogen atom and an anti-hydrogen atom behave identically from across a telescope. Their light would be indistinguishable. You'd see a star. You wouldn't know it was made of antimatter until something collided with it. And that's the first red flag. We don't see the fireworks. If antimatter galaxies were floating around in a universe full of matter galaxies, we'd expect the borders to be messy. Collisions would produce bright, high-energy gamma-ray bursts visible across the cosmos. But we don't see that. Or at least, not enough of it. Some physicists argue that this alone debunks the idea of anti-galaxies. If they existed, the evidence would be unmistakable, like finding fireworks in a cathedral. But others are more cautious. They suggest that if antimatter regions exist, they might be very far away, or isolated in the cosmic voids between galactic filaments, places where they could float undisturbed, never bumping into their matter cousins. Still, we keep looking. In recent years, astrophysicists have hunted for signs of antistars, stellar bodies composed entirely of antimatter. These wouldn't glow differently. But their cosmic rays might tell on them. When stars eject particles into space, those particles leave a kind of fingerprint. A matter star will release protons, an antistar, antiprotons, and sure enough, AMS-02, a particle detector mounted on the International Space Station, has detected more antiprotons than expected. It's not definitive proof of antistars. Dark matter decay could also be the culprit, but it keeps the door open. For a quirky twist, in 2021, a research team analysing data from Fermi, a space-based gamma-ray observatory, proposed a list of 14 star-like objects that might be antistars. Emphasis on might. The data is noisy, the signals are faint, and even if they are antistars, they're really good at not bumping into anything. Still, the possibility lingers. What if they're out there? More tantalising still is the idea of antimatter dark matter, a theoretical hybrid that proposes some forms of dark matter could actually be stable antimatter, bound in strange configurations, like antiprotons bound to dark sector particles. These would be invisible to us, neither glowing nor reflecting light, but they might interact weakly enough to persist without annihilating. A fringe too far? Maybe. But the math doesn't always say no. There's even a theory known as CP violation, which suggests that in the early universe, subtle asymmetries in the behaviour of particles and antiparticles allowed matter to slightly outsurvive antimatter. Billions of particle pairs annihilated each other, but for every billion annihilations, one lonely matter particle remained. Multiply that by the entire mass of the cosmos, and you get, well, us. It's elegant, but it's also unconfirmed. The CP violation we've measured in experiments so far isn't strong enough to explain the imbalance. Not yet. So back to the conspiracy. What if anti-galaxies are real, but just invisible to us? What if there are vast cosmic territories where antimatter reigns, simply cut off from the matter universe by distance, isolation, or even geometry? Some theorists, and more than a few late-night podcast hosts, propose a multiverse model, where our universe is one of many brains floating in higher dimensional space, and in one of those sibling brains, antimatter is the dominant form of reality. That's less science, more math cosplay, but again, not strictly impossible. And then there's the really weird take, that antimatter might not be just matter in reverse, it might be matter moving backward through time. That's a real idea in quantum field theory, by the way. According to Feynman diagrams, positrons, the antimatter version of electrons, can be modelled as electrons moving backward in time. Philosophically confusing, yes, but physically meaningful. Which raises an unnerving thought. What if the universe didn't just favour matter? What if it split it? One half moving forward, one half backward, meeting only in brief, violent moments of annihilation. You stare now into the dark between galaxies, wondering if some mirror version of you is floating out there, anti-you in an anti-ship sailing silently in reverse, never to meet except in a burst of gamma and oblivion. You wouldn't know, you'd never see it coming, so for now the anti-stars remain a rumour, a curiosity, a cautionary tale about the limits of our instruments and our imagination. But the universe still holds its secrets, and somewhere, in the quiet vacuum between theories and particles, antimatter might be waiting. Not just in labs, but in light years of hidden sky. You're floating above the Earth again now, but this time you're not gazing wistfully at the blue marble. You're squinting at invisible lines, tracing arcs of magnetism that snake around the planet like glowing threads. You're in low Earth orbit, skimming the edges of the magnetosphere, and your ship's not here to explore or escape, it's here to harvest. This is the realm of orbital antimatter collection, an idea so quietly brilliant it feels like a sci-fi background detail, but it's real, at least real enough to earn proposals, patents, and a few serious raised eyebrows at NASA and ESA meetings. Let's start with the why, because if you've been paying attention, and clearly you have, you space-sailing superstar, you already know that producing antimatter is expensive. Ludicrously so. On-Earth particle accelerators can only make nanograms per year. It's like trying to fuel a spaceship using pocket lint. But above Earth, especially in the inner Van Allen belts, nature's been quietly building up a supply of antiparticles for free. We touched on this back in section 13. When cosmic rays hit Earth's upper atmosphere, they generate secondary particles, including positrons and antiprotons. Many of these get caught in Earth's magnetic field and trapped, forming tenuous belts of antimatter particles that orbit invisibly above us. These belts aren't thick. You won't scoop out a bowl of antiprotons like cereal, but they're consistent, and that's the key. In 2011, the PAMELA, Payload for Antimatter Exploration and Light Nuclei Astrophysics, satellite confirmed that there's a small but measurable band of antiprotons trapped by Earth's magnetosphere. The density was higher than expected, especially around the South Atlantic anomaly, a quirky little dip in Earth's magnetic field where the inner radiation belt comes unusually close to the surface. It's a place spacecraft usually avoid, but in this context, it's basically a rest stop full of free antimatter donuts, so what if we could collect it? One concept proposes a small satellite equipped with a series of superconducting magnetic loops, essentially a net made of magnetism. As the satellite orbits through the antiproton-rich regions of the Van Allen belts, the loops could capture charged antiparticles and funnel them into magnetic penning traps for storage. You're imagining a fishing boat now, coasting through an invisible river, slowly netting rare, delicate fish that can explode if they touch the deck. Precision required, pressure minimal, grace absolute. It's not fast. We're talking micrograms per year. But here's the thing. That's already more than we produce on Earth. With zero fuel cost and no particle accelerator needed, just sunlight to power the magnets and patience to fill the traps. Researchers have already run the numbers. In 2012, a paper suggested that orbital harvesting satellites could yield 100 nanograms of antiprotons per year using existing technology. That might not sound like much, but if you're building microscale propulsion units, like interstellar probes or high-efficiency electric thrusters, that's enough to matter. Historians still argue whether these proposed collector satellites are a stepping stone to deep space propulsion, or just clever tech exercises with no real funding future. After all, launching a dedicated antimatter trap into orbit isn't cheap, and even once you have it, bringing the antimatter back down is questionable. You don't exactly want a payload of volatile antimatter re-entering the atmosphere with your lunch, which is why many proposals skip the return trip entirely. Instead, the idea is to use the antimatter in situ, on orbit. The collected particles would power small robotic craft, high-speed probes, or even orbital tugs designed to maneuver other satellites or debris with unprecedented precision. Imagine a tiny antimatter thruster, no bigger than a shoebox, pushing a broken satellite into a new orbit using just micrograms of annihilation fuel. No propellant tanks, no solar ion drives, just clean, elegant pulses of matter meets antimatter brilliance. And because you're already in orbit, storage becomes simpler. Space is a natural vacuum. The low temperatures are ideal for superconducting magnets. There's no atmospheric contamination, no gravity to fight against. In fact, in many ways, space is the perfect place to store antimatter. For a quirky interlude, one design called MARE, magnetically assisted radiation extraction, was proposed as a modular harvesting platform that could dock with other spacecraft. It's basically a high-tech backpack full of magnetic coils and traps, slowly collecting antimatter while orbiting Earth and then providing small propulsion bursts as needed. Think propellant Airbnb. Of course, risks remain. A containment failure in orbit wouldn't cause the same kind of destruction as on Earth, but it would still be catastrophic for the craft. Antimatter doesn't care that you're in vacuum. It'll annihilate the instant containment fails, taking out the satellite and probably a few $1 million worth of sensors along with it. Still, orbital collection sidesteps the $62 trillion per gram problem. It gives us a scalable, passive, and relatively clean way to start building up usable quantities of antimatter. And once we have a reliable trickle of supply, once these collector sats are deployed in fleets, harvesting continuously year after year, then the next step is clear. Use the same method near Jupiter, or Saturn, or even Titan, where trapped particle densities are higher and solar power still works. Eventually, these collection systems could become part of a solar system-wide antimatter infrastructure. Not just one harvester, but dozens, hundreds, feeding storage units, fueling probes, testing engines, a soft beginning for a hard future. Because no matter how advanced our engines get or how elegant our containment becomes, none of it matters without fuel. And this is how it starts. Not with a bang, but with a whisper. A magnetic loop, a quiet orbit, a trickle of antiparticles dancing through space. And one day, one of those harvested antiprotons might be the first to burn in an engine bound for Alpha Centauri. Tiny, invisible, powerful. There it is again, that equation. Hanging in your thoughts like a neon sign floating in the vacuum of space. E = mc². You've seen it 1,000 times. Maybe on a chalkboard, maybe on a t-shirt, maybe carved into a keychain at a science museum gift shop. But out here, drifting next to a reactor housing where annihilation happens on demand, it finally feels real. Because this isn't just an equation, it's not just math, it's a promise, a warning, a quiet little note from Einstein that says, everything is energy waiting to happen. And when matter meets antimatter, that equation comes alive with terrifying perfection. Let's unpack that, gently. You're trying to sleep after all. E = mc² tells us that energy and mass are interchangeable. That mass is just a very concentrated form of energy, and that energy has mass. The c stands for the speed of light, 299,792,458 meters per second. Square that number, and you get a multiplier so enormous, it should come with a seatbelt. So even a tiny amount of mass, when fully converted to energy, releases an enormous blast. And guess what? Antimatter annihilation does exactly that. When a particle of matter meets its antiparticle, they both disappear, and their combined mass is released as pure energy. Not 1%, not 90%, but 100%. No ash, no residue. Just photons, usually in the form of high-energy gamma rays and a few secondary particles. In a chemical reaction, like burning fuel, less than 1/1000th of the fuel's mass becomes energy. In nuclear fission, about 0.1%. In fusion, like in the sun, you get maybe 0.7% of the original mass converted. But in matter-antimatter annihilation, 100% conversion. That's not just better, that's the ultimate. You imagine it now, a tiny sphere smaller than a raindrop made entirely of antimatter. Suspended in a magnetic trap, it floats like a Death Star seed. Bring it into contact with an equal mass of regular matter and boom! A release of energy so vast and clean, it's the ideal from a propulsion perspective, and an absolute nightmare from a safety standpoint. Historians still argue whether Einstein ever truly envisioned the explosive implications of E = mc² when he first derived it in 1905. His original paper is calm, almost modest, like he had no idea he just handed humanity the keys to its most dangerous dream. The detonation of the first nuclear bomb in 1945 was the first time we really felt the equation. A small amount of uranium lost mass during fission, and that mass became energy, flattening a city. But that was just a fraction of what antimatter could do, a whisper compared to a scream. And now, with antimatter, we don't just release energy from splitting atoms, we create energy from disappearing them. The fire doesn't burn the logs, the fire is the log, and the match vanishing into light. Still with me? Good, let's take a breath. Picture a quiet fusion reactor, the kind we hope to build at scale in the coming decades. It uses deuterium and tritium, heavy hydrogen, to fuse into helium, releasing energy in the process. Beautiful, clean, difficult, but doable. Now imagine jump-starting that fusion with a pinprick of antimatter. Not only do you get fusion-level output, but you double dip. You also get the annihilation energy from the antimatter itself, a kind of compound energy release, where each trigger is its own tiny firestorm. That's the design behind some antimatter-catalyzed propulsion systems. You don't need to store enough antimatter to power the whole ship. You just need enough to keep lighting the match, like an engine that runs on repeated bursts of small, perfect explosions. Of course, E = mc² doesn't care whether you're using this for thrust or weapons or barbecue. The energy is released regardless of motive. Which is why, for every hopeful scientist working on propulsion, there's an equal and opposite policy analyst lying awake at night wondering how to prevent this from being used for anything else. Now for a quirky aside, in 2000, a group of physicists proposed a device called a gamma-ray laser, powered by antimatter. The idea was to annihilate positrons and electrons in a controlled cavity, producing coherent gamma rays, essentially a weaponized flashlight that could vaporize anything it touched. The good news, no one's managed to build one. The bad news, the physics still checks out. Back to our sweet little equation. The thing about E equals mc squared is that it feels inevitable. It's not some quirky invention we stumbled upon. It's woven into the universe. The same way gravity always pulls and light always moves at the same speed, the conversion of mass to energy through annihilation is just how things work. You don't get to vote on it, you just try to survive it. And for propulsion engineers, that inevitability is a gift. Because in space, efficiency isn't just helpful, it's everything. When you're trying to cross the vast, unspeakably empty distances between stars, you don't want a flame, you want a scalpel. You want a drive system so efficient that nothing is wasted. Not a single atom, not a single microgram. You want every drop of fuel to vanish perfectly in service of momentum, in service of movement. And that's what antimatter gives you. Perfect fire. Now, you float again near your ship's core. The engine is dormant. The magnetic bottle hums. Inside, a dusting of antimatter waits, silent, stable, suspended, not glowing, not ticking, just existing. A whisper of mass, a promise of light, a math equation, loaded and ready. You breathe in, you exhale, and in your head the equation pulses again, soft as a lullaby. E equals m times c squared. Out here, between the stars where even sunlight forgets to visit, you find yourself wondering, are we alone? You've been thinking a lot about antimatter, about engines, containment, gamma rays, and the occasional spoonful of doom. But now your mind wanders, as it often does in deep space, to the things we haven't built yet, and the civilizations that maybe already have. Because if we're dreaming about antimatter propulsion, isn't it possible, just possible, that someone else figured it out first? Welcome to the tantalizing crossroads of physics and imagination. Is antimatter the signature of alien technology? It starts innocently enough. We've spent decades scanning the skies for signs of intelligent life. Radio waves, laser pulses, transit anomalies. We've sent golden records into the void and listened to static like it owed us money. But if a far advanced civilization really exists, something millions of years older than us, they wouldn't be using chemical rockets or fossil-fueled boomsticks. They'd use something cleaner, quieter, more efficient. They'd use antimatter, because the math doesn't change. For them, for us, for any species trying to escape the slow suffocation of their home planet, E equals mc squared remains the ultimate ticket out. Antimatter offers the best thrust to mass ratio, the cleanest energy release, the smallest fuel requirements. It's not just a good choice, it's the only choice once you've ruled out magic and unicorn plasma. So if alien civilizations are flying between stars, there's a good chance their ships are powered by annihilation. And here's the fun twist. That might actually be detectable. When antimatter and matter collide, they release gamma rays. Specifically, high-energy photons in very specific frequency ranges. These aren't your garden-variety light waves. They're nuclear signatures, and they don't occur just anywhere. In nature, they tend to come from very violent specific processes. Supernova, neutron stars, black holes, or maybe starships. You float now beside a theoretical alien craft, not saucer-shaped, not shimmering chrome, just a clean, efficient cylinder humming quietly through the dark, its drive system flickering with bursts of controlled antimatter annihilation. Each burst emits a faint gamma signal, small, precise, recurring. If we pointed the right detector at the right stretch of sky and saw a repeating gamma pulse in those expected frequencies, not tied to any known stellar event, not located in a pulsar's heart, well, we might have just caught someone in the act of going somewhere, and we've been looking. Observatories like Fermi, Integral, and others have scanned the gamma-ray sky for decades. Most of what they see fits the models, but there are always anomalies, those unexplained spikes, those "what the heck is that?" blips in the data. A few researchers have even suggested that some of these may be the byproducts of non-natural energy use. Could it be antimatter propulsion? Probably not. Could it possibly be? Maybe. Historians still argue whether Tabby's star, a famously dimming star system, was just an unusual dust cloud or something more artificial. One fringe theory was that we were witnessing a megastructure under construction, a Dyson sphere or orbital habitat blocking out the light. Another theory? High-energy propulsion systems operating in the vicinity, producing byproducts we couldn't interpret. It's not proof. It's not even solid evidence, but it's a direction, a possible trail. Let's get a little more speculative. Some physicists have proposed that if we developed long-range gamma-ray detectors sensitive enough to spot the matter-antimatter annihilation signatures of starships in motion, we could use them to track interstellar travel even from hundreds of light years away. Think of it as radar, but for gods, a way to peek into the dark and see who else is moving. Who else has solved the problem of scale and speed and containment? There's even a name for this kind of thinking: technosignatures. Not just radio waves, but any observable evidence of technology, regardless of form. That could be industrial pollution on an exoplanet. It could be heat plumes from fusion drives. It could be gamma spikes from annihilation engines. Or if you want to get really cheeky, the lack of such signatures. If antimatter is so efficient and so universal, and yet we never detect its use in the cosmos, no gamma trails, no odd bursts, no unexplained annihilation events, maybe that's the real message. Maybe no one survived long enough to master it. Because antimatter is a double-edged discovery. Use it right, and the stars are yours. Use it wrong, and you're just a footnote in a gamma-ray burst. Still, the possibility lingers that one day a gamma observatory will flag something strange, a series of pulses spaced just so, not from a black hole, not from a quasar, but from motion, a signal not from nature but from choice, and maybe we'd recognize it for what it is, a ship, cruising, and maybe, if we're lucky, it's headed this way. For a light-hearted detour, in 2018, the Breakthrough Listen project detected a brief, unexplained radio signal from Proxima Centauri. It was likely interference, terrestrial, boring. But for a few weeks, the news cycle was electric with the idea that someone, anyone, might be trying to reach out. Now imagine that, but in gamma rays. Not a message, but a shadow, a trail, a ripple of propulsion. Not a hello, just a ship, moving. No promises, no broadcasts, just one civilization doing exactly what we dream of doing, leaving. You sit back now, somewhere between science and silence, and imagine the moment our detectors first catch the pulse. Engineers squinting at the graphs, astronomers double-checking the frequency. Gamma waves, precise and sharp, not natural, not random. And then a thought whispered across mission control. I think it's a ship. And maybe, if we're ready, if we've got our own antimatter engines whispering in the hangars, we won't just watch them fly by, we'll follow. You're drifting now through the moral vacuum of deep space, where everything is quiet except the hum of questions no one wants to answer. Sure, the antimatter drive is stable, the containment field's holding, you've just cruised past Saturn with less fuel than it takes to toast a Pop-Tart. But now, as the stars stretch out ahead of you like an open invitation, a different kind of friction begins to build. This one's not in the engine room, it's in the ethics. Because unlocking antimatter propulsion isn't just a technological leap, it's a philosophical powder keg. Once you can produce and store antimatter at scale, once you can make, trap and direct the universe's most volatile fuel, you've crossed a line, not just as a species but as a force. So tonight's question is a heavy one. Should we even build antimatter engines? And if we do, what happens when things go wrong? Let's begin with a little perspective. A single gram of antimatter, as you well remember, carries the explosive energy of a multi-kiloton nuclear weapon. Perfect, silent, 100% efficient destruction. Not radioactive, not messy, just gone. And while we've spent the last 17 sections dreaming of interstellar voyages and near light-speed joyrides, the truth is that every antimatter engine is a live weapon by design. The same containment system that lets you cruise to Alpha Centauri could, if it fails, annihilate your entire ship, or station, or launch site. No countdown, no warning, just a magnetic hiccup and a gamma-ray whisper that flattens everything. This isn't theoretical. Engineers already treat ion drives and nuclear reactors with extreme caution. But antimatter propulsion? That's another tier entirely. It's not just about redundancy. It's about building a system that cannot fail, ever, for as long as the antimatter exists. And there's no failsafe more reliable than not building it at all. Some ethicists argue exactly that antimatter should remain a laboratory curiosity, a particle physics tool, a PET scan helper, that scaling it up for propulsion is asking for extinction wrapped in chrome. Because there's another concern: misuse, not accident, intent. A world where antimatter production becomes viable is a world where non-state actors, rogue nations, mega-corporations, black market groups might someday gain access to micrograms, and that's all it takes. Imagine a suitcase with 10 milligrams of antimatter. It wouldn't just level a city block, it would vaporize it. Leave behind no radioactive trace, a clean weapon, difficult to detect, harder to stop. Historians still argue whether antimatter would have replaced nukes as the dominant deterrent had it been practical in the 20th century. Some say yes, smaller, faster, harder to intercept. Others argue the uncontrollable risk of containment failure would make them too unstable for military use. But that hasn't stopped the speculation. We already discussed in Section 12 the military's long-standing flirtation with antimatter. But what happens when the tech gets out of the lab and into the private sector? What happens when the blueprints for containment traps are downloadable? When the fuels become commodities, shipped in pressurized magnetic capsules between lunar factories and Martian refineries? It starts to look less like Star Trek and more like a cosmic arms race, and it raises a chilling scenario, the Kessler Cascade but for antimatter. One antimatter containment failure in low Earth orbit, and you don't just get a destroyed spacecraft. You get an expanding sphere of gamma radiation and plasma debris that obliterates everything nearby. Satellites, stations, communications infrastructure. It becomes a cloud of death, a no-go zone, a literal shell of orbital destruction. Repeat that failure twice, 3 times, you lock humanity out of orbit for generations. So, should we not pursue it? You float there considering. It's easy to say no when the stakes are high, but look around. Humanity doesn't back down from dangerous tools. We learned to fly even after the first planes fell. We built nuclear power even after Chernobyl. We've already walked on the edge of self-annihilation. So maybe the real answer isn't don't build antimatter engines. Maybe it's build them wisely. That means international oversight, treaties, regulations. The same way we track uranium and plutonium, we'll need global systems to track every milligram of antimatter. Chain of custody logs, sensor networks, containment compliance certifications, redundant monitoring in orbit. It also means embedding ethics into the design. Imagine a spacecraft with a built-in disposal protocol. If containment is breached beyond a certain threshold, the system automatically ejects the antimatter pod into deep space, where it can self-destruct safely. Or containment systems that degrade predictably, with visible early warning signs before failure. We're not talking about making antimatter safe. That's like making gravity polite. We're talking about making it manageable. For a quirky interlude, one speculative design from the late 1990s included biometric access to the containment chamber. Only a verified heartbeat pattern could authorize fuel movement. It was meant to prevent sabotage or accidental ignition. Probably not foolproof, but hey, you can't fault the ambition. You think again about the philosophical weight of it all. Antimatter isn't just fuel, it's potential. The potential to go farther than ever before. The potential to wipe ourselves out in a second. It's a mirror, really, showing us the best and worst of what we can do with knowledge. And so we stand on the edge, engines ready, traps charged, destinations mapped. But we have to ask ourselves, over and over, do we trust ourselves to hold this fire? Do we trust future generations? Will we teach them how to carry this power gently, or will we treat it like every other technology we've ever rushed to master? Because here's the final twist. Antimatter doesn't care. It doesn't know it's dangerous. It doesn't know it's a miracle. It just waits, in a trap, in a lab, in a satellite. And it's up to us, always, to decide what we do with the spark. You're back on Earth now, not in a lab, not in a launch bay, but in the conference rooms and cluttered offices where the future gets stalled by paperwork. This is where the dream of antimatter propulsion collides with the real world of funding applications, regulatory boards, and the ever-watchful eye of, is this even practical? The truth? We're nowhere near strapping an antimatter engine to a ship and punching it toward the stars, but the climb has already begun. Let's trace the long road from here to launch. It starts, like all revolutionary technologies, in the lab. Right now, antimatter research is thriving, not in huge visible bursts, but in precise, deliberate steps. Scientists at CERN, Brookhaven, and other institutions are pushing the limits of containment, production, and fundamental symmetry studies. They're not trying to build engines, they're trying to understand antimatter, how it behaves, how it interacts with gravity, how to keep it stable just 1 second longer than yesterday. In 2023, CERN's Alpha-G experiment finally began testing whether antihydrogen falls the same way as regular hydrogen under gravity. A trivial question. Not at all. If antimatter fell up, or even just differently, it would challenge major pillars of physics. Spoiler, it seems to fall just like everything else, but the precision of that confirmation matters. It tells us that our basic understanding is solid enough to proceed. Meanwhile, on the production side, there's quiet progress. Particle accelerators now routinely generate positrons for medical use. PET scans are already the most widespread practical use of antimatter. That's not sci-fi, that's Tuesday at a hospital. But positrons are the easy part. Antiprotons and antihydrogen atoms? Still painfully slow and expensive to make, but labs are improving yield, containment is lasting longer, magnetic traps are getting better. In 2021, alpha researchers managed to laser cool antihydrogen, slowing the particles down to mere fractions of their original energy. That might sound boring, but it's revolutionary. It's the difference between a wild tiger and one that's napping behind 3 fences. So the groundwork is there, but turning that groundwork into a spacecraft, that's a leap across a canyon. To do that, we need someone bold enough to try. Which brings us to the next checkpoint on the road: agencies and proposals. NASA's Innovative Advanced Concepts (NIAC) program has funded several speculative antimatter propulsion studies. Some were modest, probes powered by positron bursts. Others were wildly ambitious, antimatter-catalyzed fusion drives, ships that could reach the outer planets in record time. All of them ended the same way, promising, but no money for Phase 2. Same story at ESA, JAXA, ISRO. Interest, yes. Support, conditional, cautious, tied to budget cycles and headlines. Historians still argue whether this is due to scientific conservatism, public fear, or the sheer difficulty of explaining antimatter propulsion to a congressional subcommittee without sounding like a Marvel villain. Probably a mix of all three. But even without direct funding, researchers are pressing forward in tangential ways, working on beam collimation, advanced magnetic field stabilization, radiation shielding. These are all necessary technologies for antimatter propulsion, and by improving them, we inch closer to being ready, when the fuel finally becomes practical. Now let's talk about who flies first. Because when antimatter becomes viable for propulsion, someone will have to be the test pilot. And spoiler, it probably won't be a person, not yet. The first antimatter-powered spacecraft will almost certainly be a probe, small, uncrewed, built to test containment under deep space conditions and verify thrust performance. It might look like a cylinder the size of a kayak, launched aboard a conventional rocket deployed in high orbit and slowly spun up to test its micro-engine. Success? It hits a set velocity, sends data, coasts for decades. Failure? It blips off the radar and leaves a small cloud of ionized regret. But if it works, the second test won't be far behind, bigger, faster, maybe aimed at Mars or the asteroid belt. A deep space courier carrying instruments, not people. Learning how to decelerate, how to cool the engine, how to survive cosmic radiation. Only after that, after years of testing, might we consider a crewed antimatter mission. And here the questions multiply. Who goes? A national astronaut? A multinational crew? A SpaceX volunteer with a lot of nerve and a signed waiver? Or will the first antimatter-powered vehicle to carry people be built not by a government at all, but by a private company? There are whispers, concept designs buried in aerospace R&D slides, PowerPoints that never leave internal servers. But you can feel the tension. The dream is alive. And here's a quirky aside. In 2018, an anonymous concept sketch was leaked showing a theoretical, relativistic courier, a small piloted craft with a short-range antimatter drive designed for interplanetary mail delivery. Was it real? A prank? We'll never know. But someone thought far enough ahead to wonder, what if we need fast delivery between Mars and Earth? You drift now over a virtual timeline, 2025, more precise antihydrogen studies. 2030, improved space-based containment tested on CubeSats. 2040, first interplanetary antimatter-powered probe. 2050, orbital harvesting stations collecting antimatter in Earth's magnetosphere. 2070, first human-rated antimatter propulsion module. 2080, the ship leaves. It's real. It's happening. Of course, that's an optimistic schedule. Realistically, every step will take longer. There will be setbacks, crashes, Politics, outrage, funding cuts, delays, and then, quietly, progress again. Because this is how all great leaps happen. You remember when flight was impossible, when space travel was science fiction, when computers filled rooms and couldn't be trusted with shopping lists. Antimatter propulsion isn't magic. It's not destiny. It's just the next step waiting for us to find enough courage, cleverness, and cooling systems to make it work. So yes, we're far from launch. But we're also far from where we started. And somewhere out there, the first true antimatter ship is already taking shape. In white papers, in labs, in dreams. Because the future always begins as a whisper, and then one day, it ignites. Now, at last, you drift beyond the edge. Not of the galaxy, not of the antimatter containment field, but of the story itself. The final chapter of this long, slow propulsion toward the future. And yet, the view from here isn't an ending, it's a beginning. Because the world hasn't launched its first antimatter ship yet, but it will. And when it does, it won't look like the rockets of today, belching fire and thunder across a blue sky. It won't shake the launch pad or rattle the windows. It won't need a tower or a countdown or a trail of smoke to announce its departure. Instead, you'll hear nothing. Maybe you'll see a brief silent glow, an internal flare deep inside the magnetic core as the first controlled annihilation bursts into life. Maybe you'll notice a shift on a long-range telescope, a vessel accelerating not with a roar but with a whisper, clean, cold, relentless. That will be the real start of the antimatter era, and where it goes from there, that's the beautiful part. We don't know. Will we build interstellar craft, skimming toward Alpha Centauri at 20% the speed of light, leaving behind the solar system like it's a neighborhood we've finally outgrown? Will fleets of robotic collectors orbit Jupiter, harvesting antimatter like cosmic honeybees, feeding launch stations scattered across moons and mining bases? Will we one day send crewed missions beyond Pluto, beyond the heliopause, towards systems we've only ever stared at through the blur of telescopes and wonder? Possibly. Because the truth is, antimatter propulsion isn't just about speed, it's about freedom. Freedom from fuel mass, from the tyranny of orbits, from launch windows and delta V budgets and payload calculators that tell us we can't bring enough to make the trip worth it. With antimatter, suddenly space isn't a cage of math, it's a playground. You want to orbit Saturn for a year? Sure. Dive to the surface of Europa and come back up again? Go ahead. Swing by Neptune, then flip around and cruise back to Earth on the same tank. Done. And when the fuel becomes accessible, when production and harvesting mature, and we can gather milligrams instead of picograms, you won't just have fast ships, you'll have agile ships. The kind that can make detours, abort missions, return with samples, conduct long-term science, or simply, quietly, drift in the dark for decades, then fire up the drive and come home. Because home won't always be Earth. Historians still argue whether our species will ever fully leave the planet, whether space colonization is a fantasy, a necessity, or a slow form of collective insanity. But if we do go, if we build outposts, habitats, full-scale settlements on Mars-Ceres Ganymede, then antimatter isn't just a propulsion solution. It's the backbone of an interplanetary civilization. Cargo ships, emergency evacuations, medical transports, research shuttles, all moving faster, safer and lighter because they don't need to carry half their mass in fuel. Because they carry just enough antimatter to get there, and back. And the journey won't stop at the solar system's edge. One day, maybe in 100 years, maybe 1,000, the first human or human-made ship will point itself toward a nearby star, Tau Ceti, Epsilon Eridani, Barnard's star, and go. It won't need to bring fuel for the whole trip. It will collect and store along the way, refuel in orbit, harvest from the void, travel in self-contained annihilation pulses, using a few perfect atoms at a time. It might not return, but the signal will. Arrived, alive, here, and Earth will change forever. For a lighter moment, imagine the first antimatter-powered space tourism company. Branded jumpsuits, designer containment pods, 5 milligram fuel packages with expiration dates and legal disclaimers longer than the propulsion manuals. Imagine teenagers taking suborbital joyrides around Titan's rings. Imagine freight powered by firelight math. And then imagine the quiet ones, the slow, uncrewed vessels designed to outlast empires, time capsules, archive ships. One of them might even be carrying a full copy of human knowledge, riding out into the void on a drive powered by annihilation to drift for 1 billion years, just in case someone else is out there, just in case they know how to read gamma trails. Because maybe they do, maybe they already built these engines, maybe they're watching us now waiting to see if we get it right. If we can wield this power without fear, without collapse, if we can earn the right to join them not just out there, but in time. You lean back now, feeling the simulated pressure of acceleration easing you into your seat. The containment hums quietly behind the bulkhead. Everything is stable, everything is possible. Because when you distill down everything we've talked about, all the particle traps, the cloud chambers, the propulsion studies, the orbital collectors and ethical dilemmas, it all comes down to one breathtaking idea, that we found a way to turn annihilation into motion, to build ships that run on vanishing, to use the absence of matter not as a threat but as a path. So where do we go? Anywhere. And if we mess it up, we'll fix it. Because this isn't just science fiction anymore, it's physics, it's funding, it's real. The path is long, the tech is fragile, but the flame? It's there, we lit it, we caught it, we're learning how to hold it steady, and now we're ready to fly. The antimatter engines are quiet now. The ship has long since stopped accelerating, and the stars ahead are no longer blurs of motion, just steady glimmers hanging in the distance, blinking gently like they're waving goodnight. The hum of the containment field has faded to a lullaby, and the data logs have all been closed. You've seen the labs, the traps, the theoretical crafts, the planets waiting in their distant orbits. Now there's nothing left to do but float. Let the numbers settle. Let the gamma rays fade from your thoughts like old memories of impossible fire. The math was intense, the engineering delicate. But here, in this moment, none of that matters. The ship is coasting, the lights are dim, the future has been written and it looks an awful lot like hope. Out the window a nebula swirls, faint, ghost-like. The kind of beauty that doesn't ask to be noticed. It just exists, like antimatter itself, quiet, waiting, unconcerned. Maybe we'll go to Mars. Maybe we'll visit stars we've only ever traced in textbooks. Maybe one day, a ship like this will carry not just passengers, but stories, histories, seeds of new beginnings. But not tonight. Tonight we rest. The engines are cool, the stars are far, and you, curled into your capsule of warmth and blankets, are exactly where you need to be. Let the silence take over. Let the last echoes of annihilation drift away into nothing. There's no danger here, just deep space, gentle science, and dreams that travel faster than light. Good night, explorer, you've come a long way. Sleep well.